So let's welcome today's speaker, Soumitra. He is your senior, and he will be giving a talk on laser cooling and trapping of a neutral atom. He is currently pursuing his PhD from Purdue University, and he was also associated with TIFR. Let's welcome Soumitra. He will also be talking about his journey to this field. Because he was just like you, he was MSc student. So feel free to talk. Let's begin.
Okay. Yeah, thank you. Thank you so much for the introduction. So yeah, today's talk I want to make it about laser cooling and trapping of a neutral atom, because that's also my research field. And let me let me select this. Okay. I hope you are seeing the screen well and also listening to my voice. Okay. Okay. So as Nitin sir said, I was also a Mumbai University student. So just to tell you very briefly about me, is this is my website if you want to read my journey and everything. But I also did my bachelor's from Ruia College and then my master's from Mumbai University, and then I started my PhD here in Purdue in 2021 fall. So, and I am now a fifth year graduate student. Here, a PhD student is called as a graduate student. So I'm a fifth year now. And then before coming here, I also worked in TIFR. And I actually have a video on YouTube as well where I conducted a lecture series at Mumbai University. So in that first lecture also, I give details of my journey. So like if you're curious or if you want to just know about the journey, then you can watch that video as well. So very briefly, yeah, I did like bachelor's and master's in Mumbai, and then I did research in TIFR for 1.5 years or 1.3 years or 1.5 years, and then I joined for PhD in Purdue University. And since then, I have been working with cooling and imaging of neutral atoms here as a platform. And then, yeah, you can read more on the website. But in today's talk, I want to introduce you to my lab and also to my research. So I work in a research group called HoodLab, and then in HoodLab we actually work with lithium and cesium, two single atoms. So if there is a I will explain what magneto-optical trap means. So there is a term called as MOT, which is called as magneto-optical trap. So you can see in the picture that there is, let me use the laser pointer. So, sorry. Anyway, so maybe you can see my cursor. I don't know. So there is a cesium mod in the picture, which is the black and white picture in front of you. The picture has a glass cell, and then at the center of this glass cell, you can see a dot. That dot is actually 1 million cesium atoms at the center of the glass cell, trapped in a magnet optical trap. And then there is a lithium mod in the second picture, where you can see at the center there is again 1 million, like roughly around 1 million lithium atoms at the center. So this is lithium magnet optical trap, which is at the temperature of 1 millikelvin, which is very cold. And then this is cesium magnet optical trap, which is 200 microkelvin, which is even colder. And then from this ball of gas, like from this magnet optical trap of lithium and cesium, we go to single atoms of lithium and cesium, which is like 1 micron waist trap, which means that the laser is focused down to 1 micron spot, 1 micrometer spot. And then using a laser, we use that laser to trap the single atom. So there are different cooling lasers to cool the atoms, and then there are different trapping lasers to trap the single atoms and then keep them in the vacuum chamber. So since I mentioned vacuum chamber, this on the left is something that you can see how our chamber looks like. So it's a giant vacuum chamber where a giant setup, and the vacuum chamber is like this tube is in vacuum basically. So then you can see there is a there is a lot of steel and there is like a lot of parts involved here. So I will explain the parts. So there is a differential vacuum in this chamber, which means that there is higher pressure on the top and then lower pressure at the bottom. So just to give you context, on the top there is like 10 to the minus 8 millibar vacuum, and at the bottom there is 10 to the minus 11 millibar vacuum where we do the science experiment. So you can see here that so the lithium oven actually is at the top because if we want to work with lithium atoms, then we want the supply of lithium atoms, right? So then the supply we get from, let's say we have a chip and then we heat that to get the gas of lithium. So that happens at the top where you have a lithium oven to heat the lithium atoms. And when once you have a gas of lithium, then you can form a beam out of it. There is a effusive beam source type of thing that you can do, which is basically a nozzle that separates the two chambers or like the two differential vacuum systems. And then from which you can get a beam of lithium gas going from the top to the bottom. And then since it's a differential vacuum chamber, so there is higher pressure at the top and then lower pressure at the bottom. So you'll lithium atoms will flow from top to bottom. And then that's how we get them in the glass cell region. So at the bottom, you can see glass, and that's where we incident laser beams and then we interact with the atoms or like cool and trap them or even talk to them in the sense that we can image them on the camera. So that's our chamber. And then why is it tilted? Why is it at 45 like this? Is because we want optical access, complete optical access to the glass cell. So if you want to put lasers on the glass cell from all three dimensions, then putting it at one axis helps us get the optical access for like the horizontal level. Otherwise, if it was horizontal, then we would have lost one axis because we do want to interact with the atom using our lasers in all three axes, three dimensions. And that's why the chamber looks like this. So there is lithium and there is cesium, and those are the two species that we work with in our group at Purdue. So and the group is called as Ultra Cold Atoms Group, which there is a group website as well. So it's Dr. Jonathan Hood's website, and it's Dr. Jonathan Hood's group. So you can go to that website as well to read or see more pictures like this, or like just to read in general. But that's the overview of like just my research lab. So that's why I work with two single atoms, which is lithium and cesium, both alkali atoms, which is the first row of the periodic table. So, and this is my research group. And there is a postdoc, there are multiple PhD students, and you can see more on the website. These are the three publications in which I was involved. Where the first publication, I'm just telling you the overview because if you want to read about it and if you want to read the papers as well, just to know the context, what the paper is about. So the first paper is generalized cooling theory. So here we develop a theoretical model to explain how do you understand cooling of a trapped atom in a tweezer. So optical tweezer is a device where you basically focus the light down to a narrow spot, to a tiny spot like a micron size, and then you trap a single atom there. And then you incident another cooling lasers, another set of cooling lasers to cool it further down. And all the formalism regarding that, or like how to understand that picture theoretically, is there in this generalized cooling theory paper. So the second paper that we have from the lab is imaging and cooling lithium atoms. So we developed different techniques for lithium, and then we also demonstrated cooling and trapping of lithium atoms. Before us, actually, people did not trap a single lithium atom in a tweezer from a mott. So we were the first to do that, demonstrate that. And lambda enhanced gray molasses cooling is something that we used for trapping and cooling lithium. So all that technique and the results are explained in the second paper. So you can read that if you're interested in lithium. And the third paper is about cesium, which we recently published. It's also published now on in a PRA journal. So that is developing a different technique, different cooling technique in cesium. So we have experimental results with cesium, we have experimental results with lithium, and we also have some theoretical work that we have done in our lab. So these are the three papers that you can read on like, Google Scholar or anywhere, and I'm sure Nitin sir can provide you as well if you are interested to understand more about the research or more technical aspects of the research. So and before I explain the experimental results, in order for you to understand the experimental results, I think there has to be some background created, because I know in masters at least we don't have a good background of like atomic and optical physics experimentally. Like what do people care about exactly when they do research in this field? So that's why I first want to tell you a little bit about how do you theoretically understand this, or how do you model this system. So I think I talked about this as well a lot actually in the lecture series that I'm talking about, which Nitin sir and I conducted at Mumbai University 2 years back online. So there I talk about this a lot, where how do you model a trapped atom in a tweezer, or like how do you model cooling of a single atom which is trapped in the tweezer? Because once the atom is confined, it has only discrete allowed motional levels where it can go. Because imagine that if the atom is free, then it can go anywhere and it has continuous energy levels. But if the atom is trapped in a in any trap, like using light, like using lasers or using electric fields, magnetic fields, if you charge the atom, which is basically an ion, then for a species which is trapped, you have to imagine now the levels are discrete, that only specific energy levels are allowed for that atom. So that's why you have to think about the atom as a different system and the trap as a different system. And then you have to understand the laser's interaction with the atom. So there are three parts here to understand, because whenever we are modeling any system, we look at first the Hamiltonian of that system. So that's where I'm starting. And there are three parts to this Hamiltonian, which looks complicated, but it's not very complicated, since if you understand each term individually, then it's not a huge picture or like a very complicated picture. So I will explain each term individually. But there are three parts here. First is modeling the atom. So the first term here, which is nu A dagger A, is basically modeling first term here is actually nu A dagger A is the tweezer. So the first term is modeling the trap in which the atom is confined. The second term here is modeling the atom, which is modeling the two-level system. So we are imagining in this model, we are imagining the atom as a two-level system where you have a ground and excited state. I will explain. And the third term is the interaction of the atom with the laser. So in the next three slides, I have all these three terms individually explained. So let me go to those slides. But to to start modeling anything, even simulations wise or theory wise, everyone first starts with Hamiltonian. Because I think in classical mechanics, you guys must have learned that initially, we used to do everything with forces, with force vectors, because since they are vectors, it's much more difficult to model. But Hamiltonians and Lagrangians are easier to model, or like even write out and then form equations out of it. And even this is true in quantum mechanics as well, because in classical mechanics as well, we start with forces at the start, like 12th or something at that level, and then we go to energies, and then from energies, from Poisson bracket to Dirac notation. That's how you can transition from classical mechanics to quantum mechanics. And then that's why energy levels are important, because energy is what gives you the smooth pathway to go from classical to quantum mechanics. And that's why people look at Hamiltonians a lot. Whenever you see different research talks or different seminars or anything, in a lot of places where there is a theoretical talk, you will see a Hamiltonian. And looking at that Hamiltonian, people understand what's happening in the system. That's why the first step of modeling is writing down the Hamiltonian for our system. So, okay. So like I said, the first thing is modeling the atom as a two-level system. So why is this even accurate? Or why is this even relevant? So the first thing we can understand is the atom, of course, has many electronic levels. So it has a ground state, excited state, and like the most basic model also tells you that, which is the Bohr's model that you learn like even in high school. So you have different electronic energy levels, and you have all those levels are important, and all those levels are accessible depending on what energy you provide to the atom. But then when you are not providing any energy, of course, the atom is in the ground state. So why this two-level system model still works is because when you incident a laser, then you're exciting the atom to only one, exciting the outermost electron to only one excited state, which means that now if the laser is incident at the atom, then you can imagine that only two levels exist for that atom because you're on resonance with only that one level in the excited state with your one laser. So that's why you can still use this model, and it's fairly accurate if you're incidenting only a single laser frequency at the atom, and only one excited state is relevant to you for your analysis. So now imagine that the atom consists of only two levels, which is the ground state and excited state. So this is the ground state, and this is G is the ground state, and E is the excited state. So then, of course, ground state has some energy, which is how you can write it as H bar omega. So that's, let's say, the energy H bar omega is the energy of the ground state. And then this is the Dirac delta notation. Uh, so for a ground state, we will write it as G tensor product of G. And then for the excited state, we'll write it as the outer product of excited state. So excited state also is associated with some energy. So our Hamiltonian for the atom basically becomes uh, of two terms. One is the excited state energy and the excited states themselves, and the ground state energy and then the ground states themselves. So then now if we do a transformation on this, which is now you go to the frame of the laser, which means that now you are imagining you're going to a frame which is rotating with the frequency that the laser is incident at. So because why is this important or why is this useful? Is because the absolute energy levels of the atoms are not useful to us. What's useful to us is what is the difference in energy level from ground state to excited state, because that's what we are pumping with the laser, or that's what we are interacting with the laser. So when we go to the frame of the laser, then we can talk in terms of detuning, which means that what is the difference in the energy level of the ground and excited state. So if you're on resonance and if the detuning is zero, then what you're saying is your ground and excited states are the same, which means that the energy level wise, you have provided one energy to the atom to go from ground to excited state. And that's why when you transform it in rotating frame of the laser, then you can write it. Okay, imagine for simplicity that the ground state has zero energy. So then the second term goes to zero. And the first term transforms into something called like this, which means that now you're only interested in not the absolute energy level, but only the difference of energy level from the laser. So the incident energy level of the laser and the energy level which you need to excite to go from ground and excited state, the difference in those two is what you care about. That's what this delta is, which is the detuning. So that's how you can write, you can go from this simple Hamiltonian to this one. And that's why I was saying that modeling an atom as a two-level system looks like this, where you have a detuning and you, of course, don't care about the constants. So that's why in Hamiltonians, generally, when people write, they avoid writing constants. They're always there. They're kind of understood. But what the important part is the detuning, which means how away from resonance you are from the ground to excited state resonance. And this is how the term looks like when you are writing the atom as a two-level system, or when I should say when you're approximating the atom as a two-level system for your problem or for your modeling. So this was the first term of the Hamiltonian. The second term, oh, by the way, you can interrupt me anytime if anyone has a question, since I will be explaining everything, but to judge the pace at which I should explain, if there is a feedback, then I can understand better. So if at any time you think I am going too fast or too slow, please feel free to interrupt me, and then I can stop and explain more, or I can go faster as well if you want me to. So the second part of the Hamiltonian is the tweezer's Hamiltonian, which means that, like I said, tweezer is a focused laser where at the center of the focus is where we trap the atom. So how does that work? Is the atom is basically a dipole, right? So it has a positive nucleus and a negative electron cloud. So when the atom is a dipole, you can polarize it using electric field and magnetic field, or even light, because laser light is also electromagnetic field. Changing electromagnetic field is light. So when you put that on the atom, you can actually polarize the atom. And then once you polarize it, you can impart a dipole force on it. Since atom is a dipole, light does impart some force on it, depending on the intensity of the light. So when you focus the light down, of course, you get higher energy, or like higher intensity at the focus. And then that's why there is a gradient of intensity in which you can trap the single atom. That's how people trap single atoms, and there was a Nobel Prize for this discovery as well. So then, if we want to model that trap, which means that now the atom is not free to move, right? So it has discrete motional levels. If you want to model that trap, then harmonic oscillator is the best or the simplest model, because whenever you are in a trap, which means that you are in the negative or a bound potential, then close to the minima of that potential, you can always approximate it as a harmonic term, because when you are very close to the minima, you can approximate it as x square, which is the parabolic trap. And then that trap, if you write down the harmonic oscillator equation, then you can write the Hamiltonian as simply p square over 2m, which is the kinetic energy and the potential energy of the harmonic trap. Then there is a derivation to go from the classical Hamiltonian to the quantum Hamiltonian, where we write the energy levels in terms of A dagger, which I'm not going to explain, which should be there standard in any of the quantum mechanics textbooks. So then this is the Hamiltonian for a quantum harmonic oscillator, where you write in terms of A and A daggers, where you can imagine the atom is, let's say, sitting here and it is trapped over here. And this is a one-dimensional model where we are imagining that there is only one dimension and the atom is trapped in that one dimension. So then there are energy levels. There are different energy levels that you can see. And each energy level is associated with some vibration. And then the atom is trapped in uh, superposition of all these energy levels, because there are different populations in different energy levels. And also there is zero energy because the atom cannot have zero energy actually. There is some finite energy even in the ground state of this trap. So that's how you can model the external states of the atom, which is the kinetic energy part, which is a harmonic energy level. So now the kinetic energy of the atom is actually not continuous, but it is discrete. And then this is how you can model it using a harmonic oscillator. And then that's why this term comes about, where nu is the trapping frequency, which is the frequency with which it's oscillating. And then A dagger A is the annihilation and creation operator, which allows you to model this tweezer and then go from one state to another state. So adding one motional level versus removing one motional level. So this is how we can model the trap in which the atom is. So we have modeled now the atom, and we have also modeled the trap in which the atom sits. Now we want to model something called as light atom interaction. So that's the third part of the Hamiltonian, which is light atom interaction. And it seems complicated. The third term seems most complicated, but it is simple. If you imagine the dipole electric field interaction, which is the D dot E interaction that we always talk about in atom light interaction, where again there are two levels, ground and excited state, but you now have incidented one laser, which is a cooling laser. And then when you incident a laser, then you can go from ground to excited state, which means that omega determines the Rabi frequency. There is a term as Rabi frequency, where that is the frequency with which you are going up and down. And the energy that you are incidenting is a different omega, which is the small omega. And then this capital omega is the frequency with which you are going up and down. That's the frequency of oscillation. And omega square can be written as the power as well. So basically, the power that you're incidenting at the atom is modeled by omega. And then small omega gives you the frequency with which you are incidenting at the atom. So if you incident that frequency, then ground and excited states get coupled. And when the atom is in the excited state, uh, it can drop back down by spontaneous emission as well, because here in the model, in the Hamiltonian, we don't consider spontaneous emission. But in real life, there is spontaneous emission as well, which we can incorporate using a different formalism. But when modeling using Hamiltonian, we ignore spontaneous emission. But I just want to mention that there is a gamma spontaneous emission as well. When you excite anything into the excited state, any atom to the excited state, it doesn't remain there forever because it's an unstable equilibrium. So if it's unstable equilibrium, it has to couple with something else, which is vacuum fluctuations or something. So even if there is vacuum around it, it will still spontaneously emit and then come back down to the ground state, because ground state is the stable system and ground state is the stable equilibrium. So then if you want to model this atom light interaction, then you can model it using dipoles. So ER is then the dipole of your atom, which is coupling to the electric field of the laser, because light is basically changing electric field, changing electric and magnetic field. So then you can model light as an electric field and you can model atom as a dipole. And then this is how you can write down the interaction of the, so this is the electric field and then this is the interaction part. And then once you write down the interaction, then you can expand it in different terms. And the e to the power ikx goes inside. And this is one form of the Hamiltonian, but you can understand that light atom interaction is basically a dipole's interaction with an electric field. And that helps you model most of it, because the energy level 1 and 2 is basically ground and excited state. So the atom is initially in the ground state, and the laser excites it to the excited state, and then the atom comes back down via spontaneous emission or even by Rabi cycling between the two. So this is how we model the light atom interaction. And then the D operator over here, which I have not explained, is the annihilation and creation operator of the atom. So this is like one step beyond, where we are considering then atom as a discrete state thing. When we have multiple energy levels, then we can have a summation of these D operators, which means that you can go from ground state to excited state, or you can go from ground state to the second excited state, or ground state to the third excited state. So similar to what annihilation creation operators are in harmonic oscillator, there is similar annihilation and creation operator that you can create the do for atom, for atomic energy levels, uh, where you can write sigma operators, or like, yeah, I mean, the symbol is used as sigma operators, but you can basically quantize the atom as well, and you can quantize the light. Quantizing the light has A and A daggers, which is the discrete states of light. Similarly, atomic discrete states you can quantize and then write in terms of annihilation creation operators, which is sigma plus and sigma minus. So this is the third term in the Hamiltonian, where you can model the interaction. So that's how, for a trapped atom in a tweezer, this is the whole story. So if you want to imagine how the atom behaves, or how it works for a trapped atom in a tweezer, which is a focused light laser, then you can model it like this. And then this gives you now the ability to understand the system and also to simulate the system, because this is the equation of motion. So once you understand the equation of motion, then you can time evolve it. So similar to Schrodinger's equation, there is a Schrodinger's time independent equation and Schrodinger's time dependent equation. And then there are open quantum systems equations, which is like considering the environment as well. Because Schrodinger's equation is for the closed system, which is the system is not interacting with the environment. But the real world is an open system, which means that there is vacuum around it, there is other systems around it, there is leakage, there is heat transfer and everything. So you have to consider the environment as well. So the real world is actually an open system. So to simulate open systems, there is a different formalism that people use, which is called as master equation, which I will talk about. But on the zeroth level, this is how you can model the trapped atom in a tweezer, and then understand how the light interacts with the atom to understand the cooling mechanism that is happening for the single atom. So this is one part. Uh, I guess this is a good time to ask if anyone has any questions so far while I take a sip of water. If anyone wants to ask any questions, because maybe some of these terms are very new to you, maybe it's very obvious to you, I don't know. But if anyone has a question, then please ask.
Hello.
Yeah,
Are you here, Sumit?
yeah.
Yeah, Rohit has a question. Yeah.
So my doubt is, if you see the Hamiltonian, like we are taking like the sum of Hamiltonians, right? So why do you have that minus sign in that minus for the third term?
Oh, that comes, I mean, you can add a plus as well, but that depends on then what is your detuning, or like what is your convention. Because you can consider like in this part, in this omega, you can consider the electric field like charge having a minus sign or charge having a plus sign, and then put the minus sign outside. So it like you can do H0 like atoms Hamiltonian, then lights Hamiltonian, and then atom and light interaction, and then put a plus sign there and put take the minus sign inside this omega, or you can keep omega like this and then put the minus sign that is appearing because of the negative charge of the electron. So yeah, it's just a convention. You can put uh, plus sign as well, I think.
But let's see in the third term.
Sorry, what? I didn't I didn't get the question.
That HC,
Oh, HC, Hermitian
No,
conjugate.
he said
Oh, this is a Hermitian conjugate. So what you're seeing here is basically you can go from ground state to excited state, and also you can come back from excited state to ground state. So you have to consider both interactions. When you have laser incident at the atom, let's say this two-level system, the laser is not only taking the atom from ground to excited state, but it is also taking the atom from excited state to the ground state, which is not obvious. And I guess this is not always when I imagined for the first time modeling the atom, or like modeling this interaction, I did not appreciate this part a lot, that the laser not only takes from the atom from ground to excited state, but it also takes it back. So there is a cycling happening. If you are on resonance, then ground and excited state, going between ground and excited state is always happening. So
this is
uh,
simulated, right? Simulated emission.
yeah, stimulated emission. Yeah. So there is spontaneous emission and there is stimulated emission, which means that stimulated excitation and stimulated emission are happening when you have a laser incident at the atom. So what this term gives you is d dagger. If you write it in terms of just two levels, then this is sigma dagger operator, which means that you are going from ground state to excited state. And then Hermitian conjugate is basically d e to the power minus ikx, which means that it's an annihilation operator. So if you operate it on the atom, then what you're going to get is your initial state was excited state, and then you're going to come back to the ground state. So this term as a whole represents that you're cycling between ground and excited state. So that's why there are two terms, one term to go up and second term to come down from the excited state.
Thank you.
yeah, you can.
Okay, so yeah, that this is how we can model the system. And then once we have the Hamiltonian written down, then we can actually write the full thing, which is the master equation. But before going to the master equation, so if you are doing free space atom cooling, which means that the atom is not trapped, but it is free to move, and then you are incidenting laser on it, then this modeling is sufficient. You don't need to model the harmonic oscillator that I talked about, where the atom is not trapped, so the atom has continuous energy levels, and then free space modeling, you don't need the additional term, which is the A dagger A term that I mentioned in the harmonic oscillator part. But if the atom is trapped and then you want to now model the cooling, then you have to imagine that the ground state and the excited
Sumit,
state. Hello, yeah,
just
sorry.
one question. I mean, since laser cooling is being used repeatedly, I think they need to appreciate what cooling means. Because in
Yes.
this case, increase space, so cooling and increase in kinetic energy basically. Because cooling, I mean, it normally associated with temperature, then you have to define a temperature. And then question comes, how for one atom you will be defining temperature? So in what sense cooling is being used, that they need to appreciate. So can you shed light on this?
Yes. So okay. So like Nitin sir said, I guess when I was first introduced to this field, the nice introduction that I heard is whenever people think about lasers first, they imagine that lasers are associated with heat because whenever you put anything on any focused light or even shine any laser on a system, then you generally heat the system out or like increase the temperature of the system because laser has some energy and then you transfer that energy and then you get heat out of the system because lasers are also used to cut metals and like focused lasers are used to like you have also used magnifying glass to like burn paper or something. So always in our minds we think that laser is always used to heat something up, but lasers can also be counterintuitively can also be used to cool something down because like Nitin sir said, temperature, the definition of temperature is average kinetic energy. Sorry, I don't have a slide for it, so I'm going to explain it verbally. So temperature is average kinetic energy, which means that how hot or how cold you are is defined by how free or how fast you move. So then, if you restrict your movement, then that is the form of cooling that you can associate with temperature. Because so there are two things actually. For atoms which are free to move, that are not trapped, there is laser cooling for that atom as well. And there is second thing which is laser cooling for a single atom. So let me first explain the first part. So when you have many atoms going around, let's say you have atoms in a vacuum chamber, and then they're going around everywhere in all directions, and you want to cool them down to the center and then cool them down in all directions. What you do is you incident lasers from all three axes, like all three dimensions. What that does is when you have this simple cooling is actually called as Doppler cooling. It comes from the effect of Doppler effect, which Doppler effect means that if you are going in one direction and then if your laser source is coming towards you, then you see a frequency that is higher than the frequency of the actual laser because the apparent frequency is higher. If you are going in the opposite direction, then you see lower frequency. So that's using that effect, we actually interact with lasers and the atoms going in the opposite direction of the laser to uh, do cooling, which means that okay, laser light is consists of photons, which is we can consider laser as a stream of photons. So light not only has energy but also has momentum. So whenever you are exchanging light with the atom, you are also exchanging momentum with the atom. You are not only exchanging energy. So if you play with the momentum and momentum's direction, then you can actually cool the atoms down by continuously scattering light with it. And then if you do it in all directions, then using this Doppler effect, and it's a bit complicated, or like not that complicated, but like bit involved technique where you first use a magnetic field and then interact with the lasers to do this cooling. But the brief idea is that you have lasers in all three dimensions, and then you interact with the atoms from all three dimensions, and the laser's photon then transfers its linear momentum to the atom so that it pushes it towards the center. So imagine that now there is a ball of atoms, and then from you have lasers in all three dimensions, which means that all the lasers are pushing the atoms down to the center and then keeping them there. What that does is that restricts the movement of the atoms. And like we talked about, that the temperature is actually average kinetic energy. So if you restrict the kinetic energy of the atoms, that means that you can now say that the atoms are much colder compared to, or because the atoms are more restricted to move. They are not trapped in the sense that they are not in some well-defined potential. But from all axes, there is a laser incident on it, and that's why there is uh, that that cooling force is actually since lasers are hitting the atoms from all sides, that's why you get this cooling effect, and that's why the average temperature is lowered when you have these lasers on. So this is the free space cooling part, and then the second part that we wanted to discuss was for a single atom that is trapped. So now you can imagine that there is a single atom, so there is no distribution because temperature is actually average kinetic energy for a distribution. So the main question was, how can you define a temperature for a single atom? So when you have an atom trapped, then you can imagine that for a trapped atom, the kinetic energy is discretized, like we were talking about over here. So now if the kinetic energy is discretized, for a single atom, you have many energy levels in which the population can survive, which means that there is a distribution of energy levels now, and there is now not a distribution of different atoms at different energies, but there is still a distribution. So if you consider the distribution of energy levels of a single atom, then you can define temperature because temperature is average distribution. So if you see how the energy levels are distributed or how the population is distributed in these energy levels, then if you fit this to Maxwell-Boltzmann distribution, which is what we generally fit to for classical or like thermal gas, then we can define a temperature for a single atom as well. Because now when you have trapped an atom and when you are cooling the atom down, you are basically reducing the energy level of the atom, this is the external motional energy level of the atom. So you are decreasing the energy level, which means that you are trapping it more and more, you're confining it more and more, because each of these energy levels is associated with some vibrational energy. So when the atom is trapped in a harmonic oscillator trap, the atom actually has vibrational energy because it's not changing its location. It's just vibrating around that location. And that vibrational frequency is higher if it's in the higher motional state. If the vibrational frequency is lower, if it's in the lower motional state. So the lowest it can get is to the ground state, which is the lowest state over here. But it still has some frequency with which it's going to vibrate. And if you take a atom which is relatively hot and it's not perfectly cold, then it's going to be there in all these states, but it's a superposition of all these states, which means that there is a distribution. And then if you plot this distribution and fit it to Maxwell-Boltzmann distribution, then you can define a temperature for a single atom as well. And that's what we do in the lab. And if we incident light, laser light on this atom trapped in the system, then what we are essentially doing is that we are reducing the motional levels of the atom, which means that if the atom is in the 4, n equal to 4 motional level, then slowly we are taking it to n equal to 3, n equal to 2, n equal to 1. And that's what we call as cooling the single atom in the tweezer. So that's like free space cooling and the trapped atom cooling in like very short explanation. So that's why we say laser cooling. When we say laser cooling, it's either for a free space atom or for a trapped atom. Okay.
Yeah,
So this is
excellent. Thank you. You can continue.
okay. So this is free space two-level system atom. And now if you want to model trapped atom cooling, then you have to imagine, so you have to go from this picture to this picture. Because now each each electronic state of the atom has motional levels associated with it. So it's not just one harmonic oscillator, but it's one harmonic oscillator per electronic energy levels. So you can imagine that when the atom goes to excited state, it also sees an harmonic oscillator. When atom is in the ground state, it's also in a harmonic oscillator. So each electronic state is associated with a harmonic oscillator. And that's very important because when you're modeling it, you have to consider each level because you are going to start from, let's say, n equal to n plus 1 level, and then you're going to excite it, and then the decay comes back down to the nth level. And this is how slowly you can cool down to the motional ground state, because cooling ultimately means for a trapped system that you want to make it vibrate less and uh, use it to go down to the motional ground state. And that's what this diagram is showing. because the trapping frequency, the h nu, is the difference in frequency and of the energy levels of the ground state. And then ground state to excited state, there are different motional levels. So the levels you see for the, so there are only two atomic levels here, ground and excited state, but there are many motional levels. So N levels are the motional levels and G and E are the atomic levels. So there are two levels we are talking about over here. So now if you want to complete the modeling of the system, then like I said, Schrodinger's equation for our closed system state equation is not sufficient. So what you use actually is Lindblad master equation. So you already know the Hamiltonian. And like I said, for a two-level atom, the operator is simplified. So you only have G and E levels.
Hello.
Yes.
Ah,
Yeah.
now you talked about tweezers and there was a harmonic oscillator potential, right?
Yeah.
And then you introduced ground state and there is a harmonic oscillator potential. And
Yeah.
then again excited state harmonic oscillator potential. So this
Yeah.
may be a point of. So when you are talking about ground state of atom, are
Yeah.
these vibrational levels of the atom and those things? In what ways that ground state is to be visualized, that ground state itself is a harmonic oscillator, is an harmonic oscillator distribution.
Yes.
Getting the
So
point?
no. So okay, I will explain once again, and then if you still have that doubt, then I can explain again. So there are two energy levels again. So electronically speaking, the electron is in the ground state and we can excite it using a laser to the excited state. So electronically speaking, there are only two levels for the atom. But each atomic level is associated with a harmonic level because each atomic level has some polarizability. So this is going into slightly more technical language, but like each atomic level has some polarizability. Why? Because when you consider the model, then there is a positive nucleus and there is an electron cloud. So if you're in the first orbit versus if you're in the second or third orbit, you're going to have different properties as a dipole. So if your electron is in the first orbit versus third orbit, your dipole is different, which means that your trapping is going to be different. So if you have put the atom in a trap and then now you are going from ground state to excited state, it's going to have a different effect. That same trap is going to have a different effect on the ground and excited state, depending on whether the atom is in the ground state or excited state. And that's why for each atomic level, we have to consider its own motional level or its own harmonic oscillator because depending on the polarizability of the atom, like the E R part, because R is different for G and E. So that's why since R changes, this interaction also changes, and then the the trapping is also happening because of dipole interaction itself. Because there are two things: there is a cooling laser and there is a trapping laser. So trapping laser is what we are modeling by the harmonic oscillator. So I'm saying the trapping laser's effect on the atom is different when the atom is in the ground state versus in the excited state. So that's why we have to consider this model. And all these levels are the motional levels, so external levels, not the internal levels of the atom. So these harmonic levels are external potentials, energy levels. Is that was that the doubt?
Yes, please continue.
Okay. Yeah. So then now, once we have written down the Hamiltonian, there is one part still left to model it completely, which is the spontaneous emission part. So to model the spontaneous emission, what we can do, this equation looks scary, but sorry, this equation looks scary, but if you see the individual part, it's not that uh, okay. It's still difficult to explain very quickly, but what this is Lindblad master equation, and this equation is used to take into account the effect of open quantum systems, which means that if there is a spontaneous emission and the population is going to the environment, so the system is now not closed, which means that the system can exchange population and also the energy levels with the environment, which means that if there is vacuum around the atom, then the excited state can leak some population or some energy can be lost into the environment as well. So if you want to consider the effect of atom, laser, and the environment, then you have to consider this equation, which is called as Lindblad master equation. And the rho here is the density matrix. I won't go into the details of this because all this is explained and all this is also available in textbooks. But so now Lindbladian is what we consider. Lindbladian is what we consider when we want to consider the effect of the environment, which is like the spontaneous emission. Like I said, spontaneous emission is not happening because you have incidented the laser on it. Spontaneous emission happens because the system interacts with the environment, which is like vacuum or something else, and then it comes back down on its own. So to consider those effects, this equation is used. The reason I'm mentioning this is because this completes the picture. So now for stimulated absorption and emission, you have the Hamiltonian, and for spontaneous emission, you have the Lindbladian to take you from ground state to excited state and vice versa. So this modeling then gives you a full picture to simulate in QTIP. QTIP is a package in Python that you can use to write down the Hamiltonian for the system and then simulate it. So that's what people use to simulate atomic systems, and then that's how people understand what's happening in the dynamics of that system. So that's how this is like the full picture how you can model atom as a two-level system and then do cooling dynamics with it or how do the interactions with it. So this is the full thing. And you can do on your own or even like you can find simpler examples online. But maybe note down this package, note down the name of this package, QTIP. It's in Python. And then these days with ChatGPT, I guess cooling, like coding is really easy. So you can give it a try and then you can model like simple systems and then start understanding those systems through simulations. So that's actually how we also use simulations in this paper. And then we also understood the system in terms of those simulations. But the additional part, in addition to the Schrodinger's equation, is that this is the Lindblad master equation, which you can also find in like papers or even books, reference books, which I'm sure Nitin sir can provide you. But this is the full picture for the theory part. So that's why this completes like modeling of a tweezer or like modeling of a atom in a tweezer and then modeling the cooling dynamics of it. So that's why this was the first part of the presentation. So till here, if you want to discuss anything more, otherwise I am going to switch now to the experimental results in the second part. Okay. So yeah, so then the experiment part is this is how the tweezer looks like, which is basically we have a big lens and then we focus it down, and at the focus you have a trapped single atom. And then theoretical modeling, like we said, is there is a harmonic oscillator potential, and then the laser light is incident on both sides. And cooling, now you know cooling of a single atom, single trapped atom, basically means that you're reducing the motional level and then going to the ground state of the trapped atom. And this is the paper that we published. And then this is the theory paper which gives you modeling. How do you exactly model an atom and what are the different cooling techniques that are used in the model as well in the tweezer. So if you want to read more about this and if you want to get technical details of how exactly you can do modeling and understand different cooling techniques in the tweezer, because there are various cooling techniques in the tweezer, like all these are the names of the cooling techniques like unresolved sideband cooling, PG cooling. There are many cooling techniques that are used for a trapped atom in a tweezer, and then all of them have some significance and all of them are important in some sense where depending on the application, each one is chosen. And in this paper, we do simulations and we also explain each cooling technique. So if you are interested, please read this paper. Okay, so now moving to the experimental part. So I was going to explain the lithium results that we have in our lab so far. There is cesium results as well, which I will not talk about, or maybe I will talk about in a separate talk later sometime. But today I will focus on lithium. So like I said, in our lab, we have lithium and cesium. So for lithium, that this was the first paper that we published from our lab. Our lab is actually relatively new. So the lab started in 2020, which is like 5 years back. And that's why initially it was all building the system and then getting the system to work. And then for this was the first result from our lab where, like I said, lithium was not trapped before us in a tweezer directly from a mott. So we were the first to do it, and we demonstrated it using a technique called as lambda enhanced gray molasses technique. So I'll explain a little bit about that, but this is the paper if you want to read about the result and what's new about this paper. So okay, so I was just mentioning this paper, so if you want to later search about it. Okay, so now if we look at the periodic table, many of these uh, elements have been actually laser cooled and then trapped into a tweezer as well.
Pavitra, this was your PR, that was PRL result.
Yes, this was the PRL result, and then the theory paper was the PRA result.
Okay.
So yes, so then if you look at the periodic table, then there are many elements to look at, but for lasers or like for laser cooling, actually two of these columns are much more popular compared to others. The first column is the alkali atoms. So lithium, sodium, potassium, rubidium, cesium, francium is the alkali atoms. And then alkaline earth atoms, which is beryllium, magnesium, calcium, is the alkaline earth atoms. What's special in those two is that you have only one electron in the outermost shell for the alkali atoms. And then for alkaline earth atoms, you have only two electrons in the outermost shell. What that gives you is like a simple atomic structure, because when you have incidented a laser, you're only going to excite one atom if you're doing like one electron, sorry, if you're going to interact with alkali atoms. So the specialty with alkali atoms is there is a simpler structure to imagine and simpler structure to modify if you want to interact with lasers. So that's why alkali atoms are the most popular, and then alkaline earth atoms are also now getting popular. But that's why people choose alkali atoms for laser cooling or anything else, because the manipulation of that outermost electron becomes easy. If you have many electrons, then the structure gets complicated and then it's not easy to manipulate it using lasers. So that's why alkali atoms and alkaline earth atoms are preferred over any other atoms. But there are many atoms that are laser cooled and you can read about it, but I still wanted to mention this point. Okay, so we deal with lithium, which is the second, which is the lightest. So also, okay, the lithium is lightest, and then cesium is kind of the heaviest because francium is unstable isotope. So cesium is the heaviest alkali atom, and lithium is the lightest alkali atom, and that's why in our lab we have chosen these two, because later we do want to form lithium cesium molecule out of it, and when we form that, having a light versus heavy mass and also having different polarizability for both helps for dipolar molecular creation. So I won't talk about that part, but that's where our lab is headed. So once we trap and cool single atoms, we want to form molecule out of it, lithium cesium molecule, and use that lithium cesium molecule for like applications or like different like quantum physics applications, because this field is booming right now, which is like there is quantum simulation, there is quantum chemistry, and there is quantum computing. And in all three aspects, we can use trapped atoms and also trapped molecules, which if anyone wants to discuss more about that, we can talk about that later. And I'm also doing an internship right now in QRA Computing, which is a quantum computing company. So I'm here for an internship for like one semester. And that is basically the application, one of the applications of our system that we study in our lab. So it's not just fundamental science. It's also pretty much industry standard now to use laser cooling for applications. So, but yeah, we'll talk more about that, maybe discuss it later or some other time. But what I wanted to mention here mainly is alkali atoms and alkaline earth atoms are like more used than other atoms for laser cooling. So we have the lightest alkali atom, which is lithium. Of course, we can't use hydrogen. It's crazy to do experiments with hydrogen. But with lithium, now whenever you study laser cooling, you will look at the excited state, like you will look at the ground state, which is the outermost shell of the atom. So the outermost electronic level is 2s 1 half for lithium. And then the first excited state is 2p 1 half, and the second excited state is 2p 3 half. So whenever you choose a species for alkali, like for laser cooling, you always look at these diagrams, because what you're going to excite the atom with is going to be the laser for the first and second excited state mostly, because those are the easily accessible lasers are also easily accessible states. So the atom, when the lithium atom is in the ground state, it is in the 2s 1 half level. When you are incidenting a laser of this wavelength, then you can excite it to the first excited state, or you can excite it to the second excited state. And these are the levels that are, or these are the lasers that are used for doing laser cooling for lithium. I just mentioned this hyperfine, like I just mentioned this energy level structure because energy level structures is what people look at first when they want to understand the species and when they want to cool or image the species or like trap the species. So that's why these kind of diagrams are more used or like very relevant whenever you are considering any system, any atomic system for like laser cooling or something else. That's why I wanted to show this diagram once, even though I won't go into like details of these, but uh, the F levels here is basically just to give you a small technical thing, which is maybe of course already obvious to you, but why we are talking in terms of F levels is because you as an atom, you have a spin, and then as an atom, you also have orbital angular momentum. So you have S, you have L, and if you combine L and S, you get J, which is the fine structure. And then if you combine J with I, which is the spin angular momentum, which is the nuclear spin angular momentum, then you get this F. So to get this F, which is the total angular momentum of the atom, you have to combine S, L, and J. Sorry, S, L, and I, and all those combined together. There is a formalism, complete angular momentum formalism for atomic structures, which you can find in any textbook. But the final thing that you consider in the experiments is the hyperfine structure. Hyperfine meaning the F is the total angular momentum, and then the projections of F are MF states. So we have to consider and we have to exactly know which atomic state it is in. And now the states are defined in terms of F because it's the good quantum number. So what is good quantum number and bad quantum number is because when you have coupling between different angular momentum, then there is a different basis on in which you can project and then get the correct basis for the current Hamiltonian or current perturbation. So if you apply, let's say you apply a magnetic field on the atom and you apply a strong magnetic field at the atom, then you can decouple these angular momentums and then you can get a different basis as well, which is now if L and S are not coupled, then it's a different basis. So you have to consider then the atom in terms of L and S basis, like ML and MS basis instead of F basis. So these are all just different bases. I'm just giving like a brief overview, but this is how the atomic structure looks like for lithium. And these are the transitions that we use for cooling lithium in the lab. As you can see, there are bullet points here, but they are too technical, I guess, for the audience over here. So I will not explain here. But what I mean by this unresolved hyperfine structure is because it's not common to have 4 megahertz splitting in the excited state, which is very low compared to other splittings. For example, other alkali atoms generally have hundreds of megahertz splitting. Why that matters is because your laser is generally 5 megahertz wide. So when I'm saying that we are putting one frequency on the atom, it's not just one frequency, but it is a spread of some frequencies because you cannot get a laser with a line width of like Dirac delta function because there is a finite line width always limited by spontaneous emission and thermal broadening and everything else. So there is a finite width of the laser pulse that you can send at the atom, frequency wise finite width, and that width is generally 5 megahertz because 5 megahertz is the spontaneous emission line width. So your laser is 5 megahertz wide. And imagine that this hyperfine structure is 4 megahertz. So if you want to drive transitions only to 5-half state, you can't use the laser that you generally use in the lab. And that's why we need a different technique, or like we sort of have to have a different technique to do cooling in lithium, because usually the cooling that people use for other alkali atoms doesn't work for lithium very well. That's why lithium does require some other cooling technique, which is called as gray molasses cooling technique, which is the GM cooling that I'm mentioning here. And another problem with lithium is that it is also the lightest amongst all alkali atoms. Like lithium is six, basically, six is the atomic mass in it. And then cesium, for example, the other species that we have in our lab is 133. So it's like 2 orders of magnitude lighter compared to the other species. When you have a light atom, it's going to have a huge recoil. So recoil energy is basically when you are incidenting light on it and then the light bounces off, the atom is going to recoil. So that recoil energy kind of limits you in terms of what how cold you can be, and that's why cooling a lighter species is slightly more difficult compared to heavier species because you have this huge recoil. To give you context, the recoil for cesium is like 200 nanokelvin, which is like order of magnitude worse or order of magnitude better compared to lithium. So that's why higher the recoil energy, worse is the cooling for that species. So I'm just giving some technical details, but okay. So this is lithium 6. And yeah, lithium 6 is a fermion, lithium 7 is a boson, and we use lithium 6 in our lab. So there are different stages of cooling. When you start with lithium atoms, like I said, in the vacuum chamber, like this one, at the top, there is an oven. So lithium, there is a chip of lithium which we heat, that liquefies and then goes to gaseous state. And then once that gas is formed, then the beam of gas comes down. Lithium beam of cold atoms, okay, beam of atoms actually come down, and then we do laser cooling over at the bottom of this chamber. So the lithium atoms at the top are pretty hot. They are like 600 Kelvin or something. So it's like 300 degrees Celsius. So they are very hot, and then we cool them down by like 5 orders of magnitude, 5 or 6 orders of magnitude already in this chamber, and then even further. So this cooling doesn't happen in one stage; it happens in different stages. That's why I say that laser cooling of atoms happens always in stages. So the first, so coming back to the previous slide, the atoms start at 650 Kelvin temperature, and they are at okay. Another question that can come into your mind is when we say the atoms are really, really cold, like millikelvin or something, why don't they liquefy or why don't they solidify? Because generally, when you make something cool down, it changes the phase to liquid and solid from gaseous state. So, nice answer or lucky answer to that is the pressure, because we always keep the atoms in vacuum, which is orders of magnitude low pressure. And at that low pressure, you can keep the atoms in the gaseous state. And that's why when we do laser cooling, we of course need the atoms to stay in the gaseous state. And that's why we work with pressures which are very, very small. And at that low pressure, you don't get this phase transition. Okay. So at the start, you have atoms at 600 Kelvin. And then you do first stage of cooling, which is called as magneto-optical trap. And that's how you go from, which is a technique where you can see there are lasers from all three different directions, and there is a magnetic field. And how this works and everything is all available online. You can read about it, and it's also available in papers that we talked about so far. But because there is a finite amount of time in which I can explain, I can't explain everything over here, but I'm sure you can find resources to understand this technique, which is called as magneto-optical trap. So this technique gives you a ball of atoms. So when you have free space atoms going everywhere, you apply three lasers, like lasers in three directions, and then cool them down to the cloud that is colder. So then that cloud already has millikelvin temperature. So just to give you context, this is 10 to the 2. So this is hundreds of Kelvin and this is millikelvin. So it's already 5 orders of magnetic cooling. And then from here, we go to the second stage of cooling, which is then we turn off the magnetic field and then we only have lasers on, which gives you a cooling stage, which is molasses. So it's called as optical molasses. I'm just telling you terms so that you can later read about it. So the second stage of cooling is optical molasses. And then once we have very cold cloud of gas, what we do is we then coincide that gas with the focused laser. So the focused laser, at the focus, you do coincide this big ball of gas that you have, and then out of those cold atoms, only one of those atoms is picked into the tweezer. That's what we say as trapping a single atom or like loading a single atom in a single trap. So if you see over here, there are many focus spots. So there are, if you can create one focus spot, you can create many by diffraction. And then you have this single atom trapped in the tweezer. And once you have them trapped, you can further cool it down and then form molecules and then do applications with it. So this is like the journey that people follow whenever they want to do molecules or whenever they want to do even trapped atoms. They do stages of cooling, first for free space atoms and then for trapped atoms. And then they use those atoms for interactions and like quantum stuff, like quantum experiments and everything. Okay. So we do this in our lab as well, and then we get single atoms, which these two are the images from FLIR camera, which is infrared camera. Actually, this one is the from infrared camera. This is taken from iPhone because there are different laser wavelengths. So cesium wavelength is 852 nanometers, which is not in the visible part. That's why we need an infrared laser. And then lithium is in the visible region. This is 671 nanometer laser. So that's why when we take a picture with our camera, we can still see it. So that's why this is taken with an iPhone. And when we go to single atoms, of course, the fluorescence of a single atom is not huge. So the number of photons that you collect in the camera are not huge. So you need an amplification stage. So that's why single atom imaging cameras have an amplification stage where it's similar to like a PMT, photomultiplier tube, where you for a single photon you create an avalanche of electrons and then you get a big signal for a single photon. So that's why these images are taken with EMCCD camera, which is a single atom imaging camera, and then you can image single atoms as well when you map focused laser light to the camera. There is a mapping, like there is an imaging system which you can form and then map the 1 pixel to like a few micron spot in the spatial wise. So that's why you can see cesium atom here and you can see lithium atom here. Both of them are in like hundreds of microns apart. And then each trap is like a micron waste, so a micrometer. So okay, this is what we have in the lab. And like I said, first stage of cooling is the Doppler cooling. So Doppler effect, where you have atom going towards right and laser going towards left. Then you keep a frequency of the laser which is slightly lower compared to the resonance. So only the atoms which are traveling towards the laser will get excited, and then they will cool down by this collision effect, that is colliding with the photons. And those which are stationary will actually not get excited a lot. Probabilistically, the atoms which are moving will get more excited, which have higher probability of excitation. And that's why if only the moving atoms are going to collide with the photons, then you're going to get stationary atoms, more stationary atoms at the end of this process, because that's how the laser cooling works for free space. So this is based on Doppler effect, and you can read more about it. But this is the first stage of cooling, which is Doppler cooling, that you use whenever you want to trap and cool single atoms. So, and these are the magnet optical traps. Then once we have those traps, then I said that second stage of cooling is the molasses part, optical molasses part. So just to explain this image is also there in the paper, one of the papers that I mentioned. So what you're doing for laser cooling is basically you're imagining harmonic oscillator traps, and then you're going between them to do cooling. So sigma plus sigma minus is then the polarization of the laser, and then you're incidenting the laser on the atom to get some cooling. Now, since the polarization of the laser is well defined, so if you have sigma plus and sigma minus polarization, which is circular and other circular, like left circular and right circular, then you can combine different polarizations and keep different profiles at the atom. So imagine that you have linear light coming like this and linear light coming like this. So imagine one-dimensional picture in which you have linear light like this versus like this coming from two directions. Then you will form a wave of polarization at the atom. Like the polarization will keep changing at the atom because there is a superposition of two different polarization states. And then at each level, uh, okay, since at light can be modeled as an electric field, polarization can be also modeled as a part of that electric field, which is called as a phase of that electric field. So when you have light going from one axis to another axis, like counter propagating to each other, then you can create this standing wave, and this is the standing wave that you create. And when you have atoms in that standing wave, of course, depending on light's polarization, the atom will see a different structure, or the energy levels of the atoms are going to change depending on what polarization you have at the atom. So that's why the atom's energy levels, as you can see in the diagram, are going to do like this, are going to go like this, because your light is now having different polarization at each point in space. So what you're doing over here is you're modulating the ground state energy levels. And by modulating the ground state energy levels and then keeping the cycling transition going with ground and excited state, then you can cool down further, and this is called as optical molasses, or this is also called as polarization gradient cooling, which is because this is forming a gradient of polarization. And there is a different cooling technique, which is gray molasses cooling technique, where you also have dark states, because you can create dark states by two things. Uh, I guess again, going without going into further details, those are states where if the atom is in that state, then it would couple with the laser. So if the after bouncing off laser light, if the atomic population is changing between different ground states, then it can go to a ground state where it will stop interacting with the laser. That's what people call as dark states. And the bright states are where atom is still interacting with the laser. So depending on which atomic level the atom is in, which atomic level the electron is in, it will either interact with the atom, it will either interact with the laser, or it will not interact with the laser. If it interacts with the laser, it's called as bright state. And if it doesn't interact with the laser, it's called as dark state. And you can create these dark states by various techniques. But the important point here is that gray molasses technique uses these dark states, and polarization gradient cooling doesn't use the dark state. So these are basically just two cooling techniques that are used for an atom in a tweezer, and they are much more complicated to explain in like a couple of minutes. But I guess just to keep these names in mind and like just the formalism in mind. And by the way, the paper explains these techniques in detail. So if you want to read about them, then please do read the paper. But this technique is the one that we use for lithium. So let me go to the results with this technique used in lithium. So actually, just to show you a quick video, how the single atom trapped on the camera looks like. Uh, it's okay. Like the video is, since the video is not working, you can look at the picture. What the video had was actually the light that is shining, that we are shining on the atom, and this one pixel is where you can see the single atom is shining back. Because when you are incidenting laser light on it, it scatters, and then we collect the light on the camera, and that's how we image the single atom. And here in this dark pixels, you can see one bright pixel where there is a single atom. So that's the single atom in a tweezer. Oh, the video is working nice. So you can see the light is actually blinking. Like the you can see it again that it's also actually blinking. So it's not always there or it's not always shining, but when it's getting loaded and when it's shining, when it's scattering the light, then we are able to see the atom. So one last time if you want to see the video. Okay, so this was single atom trapped in the tweezer, and we are shining light on it to get the image back on the camera. And when we shine light on it, if we do this continuously, then in one shot we are going to get one picture. So then in that one picture, if we see how many photons we collect, then this is how we can form the histogram of a single atom, which means that if your atom is not there, you're still going to scatter some light. So you're going to get some light at the camera because the laser bouncing around the walls and everything is going to give you some stray light, some ambient light. So if you collect the number of photons on the camera, then you're going to collect some histogram like this. Like because at at each point or at each experiment, you're not going to get the same number of photons. You're going to get different number of photons. So that's why there is a distribution that you can find. So for each experiment that you do, if you collect the number of photons, then if the atom is there, you're going to get additional photons because the atom is scattering additional photons or emitting additional photons. So then when you don't have an atom, you're going to get less photons. And when you have an atom, you're going to get more photons. But each time you do an experiment, then you can take an image, take a shot, take a single shot image, and then plot the histogram and see how many times you did collect a single atom, or like you were able to image the single atom, and how many times you were not able to image the single atom. So then this line gives you the cutoff. So this is basically before this line is everything is background. And then when the atom is there, it's going to give you additional photons. So that's why we are going to get more photons. So if you do this continuously, then we form a histogram like this, where you get this peak. This peak determines, or this peak represents single atom in the image, and this peak represents that there were no single atoms in that experiment. So if you repeat this 1,000 times, then you're going to get a distribution where, like, let's say 500 times we had a single atom and 500 times we did not have a single atom. So histograms are another things that you're going to see a lot if you read single atom imaging papers and imaging and cooling papers, because that's how we understand if the atom is there or not, looking at this histogram. So we are basically repeating the experiment 1,000 times, and each time there is some amount of photons that we collect on the camera, and that's what I'm calling as imaging histogram. Okay. And like Nitin sir said, that for a single atom, we need to define a temperature. So how do we determine the temperature of a single atom? Is that since it's in a trap at some temperature, we release it for some time and then we recapture it back. What that does is, if the atom is really hot, then after releasing it, it goes very quickly away from the trap. Versus if the atom is really cold, then it really goes slowly away from the trap, which means that after a few microseconds, you will still be able to recapture it back. So this is one technique to experimentally determine the temperature of the atom, whether the atom is cold or not. So since you have the atom in the trap, release the trap, like turn the trap off for a few microseconds or something, and then turn the trap back on. If your atom is colder, then you will be able to trap it for longer. Like you will be able to release it for longer and trap it back. If your atom is hot, then you're going to release it and it's going to immediately go off. So then if you plot the distribution, if you plot how the time looks like when you release the atom, if you're going to release it and then match it to the Maxwell-Boltzmann distribution again, the distribution that you will get, because the population will not be in one of the motional levels. The population will be distributed in different motional levels. So that distribution, if you match to the Maxwell-Boltzmann distribution, you're going to get a temperature. And that's how people extract temperature of a single atom when they quote anything in the paper. They just release the trap, they just release the atom, and then they capture it back. This is called as release recapture measurement. So you can do simulations and you can also map it to the experiment, saying that, okay, lithium atom is at 10 microkelvin or like 60 microkelvin or something like that. So this is how we get the temperature from a single atom. And okay, just to show you briefly the results of lithium, we were able to take the image of lithium. This orange line on the first graph shows you if there is no cooling applied, then we are able to take only 1,000 images. But if we apply a cooling light, then we are able to take many more images before the atom dies out from the tap. So each image per, I'm just giving you numbers so that it's quantitatively in your head. What do you mean by imaging a single atom? So each image takes like 15 milliseconds. So you shine laser at the atom for 15 milliseconds and then collect light that is scattered from the single atom. So that happens for 15 milliseconds. What I say, there are different meanings for imaging fidelity and survival. It's basically giving you how good the imaging is, how good you can, if the atom is there in a tweezer, how good you can see it. So like if the atom is there, then out of 1,000 experiments, you can miss it like 3 times or 5 times. That's what basically this means. And survival means that if you image the atom, which means that if you incident light, laser light on the atom, then will it stay there or will it go away? So that's called as imaging survival. And then 99.95% survival basically means that if you image for 1,000 times, only 5 times the atom will go away. So this is the imaging survival. So we were able to image a single lithium atom, keeping it there for 60 seconds using this gray molasses cooling technique. And then we said how we looked at how the histogram is formed. And once the histogram is formed, this is how the histogram looks like, where if the atom is there, then we get this peak. If the atom is not there, then we get this peak because there is always a Poissonian distribution. Since this is discrete and random, it is Poissonian distribution. If it is continuous and random, it is Gaussian distribution. So the distribution of photons that you get at the camera with the single atom and without the single atom is both a Poissonian distribution, since discrete randomness gives you Poissonian. So there are different parameters here as well that we tune to. There is the potential has a depth as well, like in which the atom is there. And the technique that I showed talked about in the previous slide, which is release and recapture technique, where you just hold the atom and then release it for some time and then capture it back. This gives us the quantitative part to assign some temperature to the single atom. So that's how we say that the atom is at 70 microkelvin, 100 microkelvin, or 600 microkelvin. So 600 is without any cooling, and with cooling, we are able to cool the lithium by an order of magnitude. So keeping the lithium atom there with the cooling pulse, we are able to cool it down by an order of magnitude, which is really good. So with lithium, people were not expecting such good cooling results, but then since we found them, we also tried to explain them using theoretical formalism. That's why we have this theory paper out as well. So these are the lithium in a tweezer results. I know I was not able to cover a whole lot in detail about the experimental results, but I think at the background, since I had to bring you to a background to understand the results or even like appreciate the field, I wanted to give first a brief overview of the theory, and then I wanted to just showcase some highlights or some results so that later you can read on your own the results. Of course, the paper is out. So, and it's also a, a work that we did 2 years back, and currently we are working with cesium in the lab. So you can read about that as well. But these are the imaging and cooling results with lithium, and it was very special. It was very exciting to work with lithium, and also working with two species in one lab, like two single atoms in one lab, is also pretty special. So it's a great opportunity for people when people get this opportunity. It's really nice. So this field is amazing, and this field is booming as well. And like I said, I am on an internship right now. So this field also laser cooling and atom trapping is also having applications in quantum computing and like quantum simulation. And this field right now is really exciting. So if you are interested, uh, if you want to if you want to discuss more, and if you want to do research in this field, then I'm happy to talk about it. This is my LinkedIn profile. So in case you want to connect with me on LinkedIn, then I am more than happy to connect with you. And also, you can message me on LinkedIn as well. I am fairly active on it. I also have a personal website on which you can read more. There is also a group website, hoodlabpurdue.com, where you can go and read about our research. But I'm open to questions now, since and any other discussion that you guys want to do, because this is what I wanted to cover in the talk. And yeah, so I'm open to questions if anyone wants to ask any questions. But thank you for taking time.
Thank you, Sumit. Can you tell more about this quantum computing route with this laser cooled atoms? There are various routes of quantum computing, photonic routes, photonic routes.
Yes,
What's so
yes.
special about this phenomenon?
So uh, I can actually tell a little bit in detail. Let me share a different screen. Um, Let me see, because I do have a presentation that presentation slide will help a lot to explain this thing. Mm, okay, so I'm going to share again. Mm, Zoom, share. Um, wait, or did I share the same thing? Wait. Uh, okay, can you see this quantum computing hardware
Yes, yes,
thing?
yes, yes.
Okay. So let me. Yeah, so like you said, there are many modalities that are used in quantum computing, and there are various types. So yeah, there is a bit and there is a qubit. So maybe everyone is familiar with this, that quantum computing is basically you can create superposition of zeros and ones, and that gives you enhanced ability to do more than what classical computers can do. So you need what you mean by that is you need a qubit, meaning that since in classical computing you need one and zero, which is a transistor. In quantum computing, your transistor can be a qubit, or like the needs to be a qubit, which has two additional properties, which is you need a superposition, you need superposition in your system, and you also need entanglement. So what superposition is when you have two levels in your atom or any qubit that you take, and then you can do superposition with that, meaning that the atom can exist or the population can exist in both levels at the same time. So if you have multiple energy levels, then superposition of those multiple energy levels, meaning that the population can coexist in many of these levels, or you can interfere those levels. That's called as superposition. So in one atom, if you have many energy levels, that is superposition. But if you have multiple atoms, then having information among those two different atoms, which are two different atoms, not the same atom. So energy levels of two different atoms, if they are coupled, then that is called as entanglement. Because, okay, at least I was confused about this point previously, that what is superposition and what is entanglement. Superposition is when you have one system, one atom, and then in that atom, if there are multiple energy levels, if they are connected somehow, that is superposition, and then two different atoms connected, having connected energy levels, is entanglement. So if you have these criteria, then you can choose your physical qubit, and there are many choices for physical qubit, similar to the transistors in classical physics. And there are different choices. The different choices are, let me go to those choices. Yes. So there are all these modalities. So you can use a superconducting qubit, which is a superconductor that basically it's a LC circuit where you LC circuit has a harmonic frequency. Like LC circuit has a resonance frequency, and then that resonance frequency is one frequency. So it's like a harmonic oscillator. So it has many energy levels. So harmonic oscillator has many energy levels. What you need is a two-level system, right? For a qubit, you need two-level system, which means that you need a non-linear harmonic oscillator, meaning that you need only two levels of those all the energy levels that are there in the harmonic oscillator. So what people do is they transform or like they go to a circuit which is LC circuit but a non-linear LC circuit using superconductors uh, so that they can form something which is similar to a qubit, which is like has only two levels which are dominant and all other levels are not important. So superconducting qubit is basically an engineered qubit, which means that the original system doesn't have two levels, but then you create a system that has two levels and then use that as a qubit, which are for quantum computing. Or you can use ions. So people also do trapped ions, um, which is like you could take out one electron from a atom and then that becomes an ion, and then you can trap it and cool it down using electric magnetic field and lasers similarly. So that can also be used as a two-level system, ground and excited state, and that becomes your qubit. Then you have neutral atoms, and neutral atoms can also be qubits. Then you have photons, topological qubits, spin defects. There are many multiple modalities. But just to give you a very specific classification out of those, is there is an intrinsic two-level system that you can use. Let's say nuclei or electrons. Or photons, because photons inherently have two polarizations, let's say horizontal and vertical polarization, or sigma plus sigma minus. So there are these two states which are the system itself has two states, like electrons, the spin of electron can be plus half or minus half. So then a photon is 1 and 0. So then you already have two states. You don't have more than two states. So intrinsically, if you have two states, then you can actually do two-level system and you can do that. So that's why it's called as natural qubit. Then there are systems which are not two level, but you can focus on two levels and ignore everything else if you are just interacting with those two levels. So that is then your atoms, ions, and molecules, because inherently you have multiple levels. But you, ultimately for quantum computing, you only require two levels, right? And then you need superposition, entanglement, everything. So the two-level subsystem is then this atoms and ions. And then the third category is the engineered two-level system, which is like spin defects or like superconducting qubits, which is where you are creating two levels, and there is no inherently two-level system in your case, but you are creating that system entirely, and then you are making an effort to make all of them identical. Because if you have atoms, then you already have identical two-level systems in your quantum computing. But then for a superconducting qubit, you're creating this qubit, this LC circuit, which is not something inherently two level or not something physically like two level, anything that's two level about it. But then you're uh, manipulating it such that you can create a perfect two level system out of it. And that's why there are many different classifications or qubits to choose from uh, like for quantum computing. And there are many articles, like review articles and everything on this, which if you want the name, then I can show you a name for superconducting qubits. Uh, so this is one of the labs at Purdue, uh, which you can go and read about. This lab also has good explanation, and it has papers which are publishing papers on superconducting qubits. This is how the computer looks like for superconducting qubits. Quantum computer looks like this. This is the Ma lab at Purdue. There are many different labs that you can read about, but this lab also has good papers on superconducting qubits. And then trapped ions, of course, you can of course find good review articles to understand this field better, but there are a few groups that are working on this. And there is this neutral atom platform in which I work on, where you have a vacuum system and then you have trapped single atoms as your qubits. So there are multiple modalities that you can use. And there are now even companies that are doing this thing. So yeah, I just wanted to share what people have and what people don't. And these are, yeah, if you want review papers, then these are actually two good review papers that you can read to start with the field, to understand the field and quantum computing to be specific. Yeah.
Yeah, thank you very much. So with this, let's thank our speaker for today, Soumitra. Thank you very much.
Thank you. See you.
Bye.
Bye.
Thank you, Soumitra. Thank you.
Okay, yeah. See you. Bye.